Alright, so let's look at equations of simple harmonic motion. In our previous slide, we said that displacement for simple harmonic motion is given by the formula y, which is a function of time, is equal to the amplitude sine, bracket open, the angular frequency times time plus the phase angle or constants. Alright, so this is the equation for a simple harmonic motion in the y-axis. Remember that this is the time. Now, to find the speed or the velocity of the displacement, we have to differentiate displacement with respect to time. And when we differentiate displacement with reference to time, which is written as this, the speed or velocity equal to displacement over dt. This means that we are differentiating displacement with respect to time. When we do that, our velocity becomes v equal to the amplitude times the angular frequency cos angular frequency times time plus the phase constant. Now, what I did here is that I differentiate my displacement to get my speed. Alright, now the reason why we have a cos here is because when we differentiate sine, it gives us a cos. Alright, so you can refer to your differentiation tables for how to differentiate. Meanwhile, in your math 2, you'll be doing more about differentiation. Now, to get the maximum velocity, what we do is that becomes v mass or v subscript mass is equal to amplitude times the angular frequency. So this is the formula we use for the maximum velocity. Now, for the acceleration, we have to differentiate the velocity. So we can say that acceleration, which is a, is equal to differentiation of the velocity over time. So this means that we are differentiating the velocity with respect to time. And when we do that, we get the acceleration becomes equal to negative amplitude omega squared, cos becomes sine, open brackets, omega t plus the phase angle. So this is the formula we use for finding acceleration. In fact, the reason why we have a minus sign here is because when we differentiate cos, it gives us minus sign. That is how we got the negative sign. In fact, in your second semester, you will understand better what we are doing right here. Now, to get the maximum acceleration, becomes the A mass is equal to negative A omega squared. Negative A angular frequency squared. So this is the equation for finding the maximum speed for a simple harmonic motion. Now let's look at the first law for simple harmonic motion, after which we'll look at two questions. Let's look at the first law for simple harmonic motion. Now we recall that from Newton's second law, we are told that the force is equal to ma, which is F is equal to the mass times what? Acceleration. Good. Now if we relate these to simple harmonic motion, we are told that acceleration for simple harmonic motion is equal to minus a angular frequency squared sine angular frequency times time plus the phase constants. All right, now we can replace our acceleration here with this equation, so it becomes the force equal to the mass. We take off this acceleration, it becomes negative. We have negative a omega squared sine angular frequency times time plus the phase constants. Now if you look at this equation, you see that a sine the phase angle is the same as our displacement right here. Yeah, this is right here. So we can see that if you recall that our displacement, which is y in this case, is equal to a, the amplitude, sine omega t plus the phase constant. Now that means that a sine the phase angle is my displacement. So therefore I can rewrite this equation, becomes the force equal to negative the mass amplitude, or let me write the angular frequency squared, a sine omega t plus the phase constant. Now what I'm saying is that this is my displacement, so therefore I can say the force is equal to the mass angular frequency squared. I will take off this and replace with my displacement y. Good. So we can relate this equation to another equation, which is the force law, and we can also replace it with the Hooke's law. And you all know that from Hooke's law we are told that the force is equal to a negative kx, where k is the spring constant and x is the displacement. So as you can see, my x here is the same as my y. All right, so x is the same as y, so because x is displacement and y is displacement, so I can replace my x with y, so f is equal to negative kx. The reason why I replace my x with y is because in this case we are working with displacement. My y is displacement, my x is displacement, so they are the same thing. So what I do now is that I will equate this to this. So therefore we have negative k y equal to negative mass omega squared y. So what we do now is that I want to make my angular frequency the subject. So as you can see, the negative sign cancel out, the displacement cancel out. So I'm left with K equal to the mass times the angular frequency. Now I want to make the angular frequency the subject, so I can say that the angular frequency squared is equal to K over the mass. Therefore, my angular frequency is equal to the square root of K over N. So this is a very important formula we use for simple harmonic motion, where K is the spring constant and M is the mass and W is the angular frequency. Now, if you recall, we said that the period or the time period was given as 2 pi over angular frequency. Recall, time period. All right, so we were saying that time period was given as 2 pi over the angular frequency. I hope we all remember that. That's the time period T is equal to 2 pi over angular frequency. Now I can enlarge, or I can express this time period in a different way, because now I know that my angular frequency is equal to square root of K over M. So therefore I can substitute K over M into this equation. So we now have 2 pi over, now omega becomes square root of K over M. All right, so therefore I can say that my time period T is equal to 2 pi divided by square root of K over N. Now, you know, in maths we can express this further. It becomes 2 pi times, so when we change division to times, we have to flip this right hand side. It becomes square root of the mass over K. So therefore we can say that time period is equal to 2 pi square root of mass over K. So here is another formula we can use to solve for time period when given questions. We shall be looking at 2 questions of how we can apply these 2 formulas. Let's look at the first question here. Now here is the first question. We are asked, or we are given that the position of a particle along y-axis is given by x equal to 0.85 sine, bracket open, 24t plus 0.7 meters, where t is time in seconds. A, what is the amplitude and the period of the motion? And B, we are asked to find the position, which is displacement, also to find the velocity and acceleration at t equal to 0.25. Step 1, I have to write out the original equation, which is y equal to amplitude sine omega t plus the phase angle. That's the first thing we do. Now in the question we are given that x is equal to 0.85 sine 24t plus 0.7, yeah, or in meters. Now from these I can equate both equations. So I can say that my amplitude is what? 0.85. So my amplitude A from the equation, when we compare the general equation with this given equation, I can say that my amplitude is what? 0.85 meters. That is my amplitude, 0.85 meters. That's correct. Now, when we compare the equation again, we see that our omega W is giving us 24. Angular frequency is what? 24. All right. From this, we can find the period. Now, I have known my amplitude. What next is to find the period. And please remember that the unit for angular frequency is radians per second. Okay. Now, let's find the period, and we know that to find the period, P is equal to 2 pi over the angular frequency. This should be T. The period is giving us T. So we now have 2 pi divided by 24. So therefore 2 pi over 24 will give us, our period becomes 0.26 seconds. So the period is 0.26 seconds. So that is our answer for the period. So we've answered question A. Now for question B, we're asked to find the position. Now the position is the same as the displacement. So let's find the position. To find the position, we have to use this formula because we are told that time is given as 0.25 seconds. So we can say therefore that our position, to find the position, is S or X equal to 0.85 sine 24 times time. My time is given as 0.5 plus the phase angle is 0.7. Okay. What next? We now have 0.85 sine. When you put this in your calculator, you should get 6.7. 6.7 bracket close. So therefore, we have 0.85 times. Now to get the sine of 6.7, you have to set your calculator in radians, otherwise your answer will be wrong. So you have to put your calculator in radians for you to get the correct answer. So sine 6.7 will give us 0.4048. 0.4048. Now the reason why we use radians to find the sine, because this angle here is a phase angle, and when we know phase angle are in radians, so that is how we put that in radians. So please don't forget that it must be in radians for you to get the correct answer. So 0.85 times 0.4048, therefore my position is giving us 0.3 meters. That is the position of the motion. The next thing again, we are asked to find the velocity. We give us the formula for velocity. It's giving us V equal to the amplitude times the angular frequency cos omega t plus the phase constant. So what we do now is to put in the values. So therefore my amplitude becomes 0.85 times the angular frequency, which is 24, cos omega is 24 times the time is 0.25 plus the phase constant is 0.7. Okay, good. So what next? We have 0.85 times 24 cos. When you put this in your calculator, you should get 6.7. Bracket close. What next? So therefore we have 0.85 times 24 times cos 6.7. In this case, you also have to ensure that your calculator is in radian. So cos 6.7 will give us 0.9144. 0.9144. So therefore our speed for this motion is 0.85 times 24 times 0.9144. That gives us 18.7 meters per second. 18.7 meters per second. That is the velocity of the motion. So let's look at the acceleration of the motion. Now we are given the formula for acceleration. The acceleration. Remember, we said that for the acceleration, the formula is giving us A equal to negative A amplitude, this time omega squared, sine, open bracket, omega t, plus the phase constant. So what next? We log in the values. So we have negative amplitude is 0.85 times our angular frequency is 24. This time is squared, 24 squared, sine, open brackets, 24 times our time is 0.25 plus the phase constant, which is 0.7. Bracket close. Okay, so therefore we have negative 0.85 times 24 squared gives us 576. Sine, when you put this in your calculator again, you should get 6.7. So therefore we can see that negative 0.85 times 576 times sine 6.7. If you recall, sine 6.7 gives us 0.4048. So sine 6.7 is 0.4048. 0.048. So therefore the acceleration for this motion is negative 0.85 times 576 times 0.4048, which gives us negative 108.2 meters per second squared. So here is our final answer to the question. Here is another question. It says a 6 kilogram collar is attached to a spring of spring constant 550 Newton per meters. It slides without friction over a horizontal rod. The collar is displaced from its position by 25.0 centimeters and released. Calculate the period of oscillation, and B, the maximum speed, and C, we have to find the maximum acceleration of the collar. Now the first thing I do here is that I have to write out my given data. I'm given the mass. The mass is 6 kilogram. I'm giving the spring constant K is given as 550 Newton meter. Okay, I'm giving the displacement. In this case, this is my amplitude. All right, so I'm giving the displacement, which is amplitude. Remember that we said that amplitude is the maximum displacement of an object. So this is our displacement. It says the collar is displaced from its equilibrium position. That means that this is our amplitude, which is 25.0 centimeters. Remember, we have to convert to meters, so it becomes 25 divided by 100. That gives us 0.25 meters. So we divide 25.0 over 100, and that gives us 0.25 meters. Okay, so what we do now is to find the period of oscillation. A, let's find the period of oscillation. To find the period of oscillation, we use the formula which we derived earlier, which is T equal to 2 pi times the square root of the mass over the spring constant. All right, so what we do now is we log in the values. So therefore we have 2 pi times the square root of the mass. The mass is 6 over the spring constant is 550. So therefore my period becomes 2 pi times the square root of, now 6 divided by 550 gives us 0.01091. So therefore my period of oscillation, if we put that in our calculator, should give us 0.7 seconds. 0.7 seconds. So that is the period of oscillation. 2 pi times square root of 0.091 should give us 0.7 seconds. So as you can see, it's very important. What you have to do is to remember the formulas. Now the next thing we do now is to find the maximum speed. To find the maximum speed, we use the formula again. Remember, we gave us a formula for the maximum speed, and we say that maximum speed is equal to the amplitude A times the angular frequency. Good. And please remember that we said that the angular frequency is equal to the square root of k over m. All right, so we can use this in this formula. We have the maximum speed is therefore equal to the amplitude A times the square root of k over m. So therefore, we have amplitude, which is 0.25. So my amplitude is 0.25 times the square root of k is 550 divided by the mass is 6. So therefore we have 0.25 times the square root of 550 divided by 6 gives us 91.67. So therefore, the maximum speed of this oscillation is 0.25 times the square root of 91.67 will give us 2.4 meters per second. So that is the maximum speed. So the last question is to find the maximum acceleration of the color. Now, to find the maximum acceleration of the color, which is c, we know that the maximum acceleration is equal to negative omega squared times the amplitude. All right. Now, we also know that that omega squared is the same as k over m. I hope we remember that equation. So therefore, I can therefore say that omega squared becomes k over m times the amplitude. Now, the reason why I ignore the minus sign is because I am looking for the maximum acceleration, which means that the oscillation is on the positive y-axis. So we don't have to include the minus sign because it's at the maximum displacement. So it should be positive. So that is why I have to ignore the negative sign at this point. So what I do next is that I will log in the values. My spring constant is 550 over the mass is 6 times our amplitude, which is the displacement, is 0.25 meters. All right, so therefore our maximum acceleration, 550 divided by 6 will give us what? That gives us 9.67 or 91.67 times 0.25. So therefore, our maximum acceleration is 91.67 times 0.25. That gives us 22.9 meters per seconds squared. So that is our maximum acceleration of the color. Okay, so I want you all to study these concepts very closely, and you are asked to do this assignment. Here is an assignment for us. Please, you are to do this assignment on a piece of paper and take a picture of this of your work and submit on or before the 8th of December to this email address. Everyone is expected to do this assignment on or before the 8th of December. So thanks for watching this video.